Hey everyone, welcome to this unit introduction to the first unit of the spec course. This is a simple proofs topic, and I think it kind of sets a theme for a lot of the Year 11 specialist course, which is very proof heavy. And so in this video, I'm going to be going over simple number proofs, direct proofs, introducing you to mathematical statements first of all, before I move into those proofs. Have a look at direct proofs, I have a look at proof by contrapositive, proof by exhaustion, which is a slightly more complex form of a direct proof, and I also have a look at proof by contradiction. So this is basically the unit outline here. So I introduce you to mathematical statements, about implication statements, that is conditional statements, and kind of variations of conditional statements like converses, negations, inverses, and contrapositives. And then I also have a look at equivalences, which have a kind of tie-in with converses. I then have a look at, I'm going to skip proof by contradiction because I'd say that's a more formal and systematic proof. I kind of have a look at some mathematical symbols that you can use to represent statements that are written in a worded way to kind of shorten writing them. I have a look at examples and counterexamples. I have a look at direct proof, proof by contrapositive, and proof by exhaustion, which aren't directly listed here, but are an important part of this unit. And then finally, I'm going to have a look at proof by contradiction, that 1.1.2 point. I have a look at that last because, like I mentioned before, it's a bit more of a systematic and formal proof than direct proof or proof by contrapositive. So let's get straight into the video then. Okay, so the first thing I want to do is introduce mathematical statements, and more specifically, I want to introduce the concept of a conditional statement, that is one event implying another event. So the way we represent a conditional statement is P as one event implying a second event Q. That is, if an event P occurs, then an event Q follows. Okay, and in the context of a conditional statement, we consider P the hypothesis, and we consider Q the conclusion. We can also refer to P as the precedent and Q as the antecedent. That is, it is the thing that logically follows after event P has occurred. Okay? So when we consider conditional statements, one such example that we could use is, for example, the event P is the event that it is raining, and the event Q is that the grass is wet. Okay? And we can see that this statement is true, right? So if it's raining, the grass is wet. Okay, so that is a true statement. Now, a big important part of mathematical statements and conditional statements is knowing the sort of logical relationships between the original statement and variations of the original statement. And more specifically, we talk about the converse of a statement. We talk about the inverse of a statement. We talk about the negation of a statement, and we talk about the contrapositive of a statement. And so when I say converse, what I mean is flipping the hypothesis and the conclusion. That is, in this case, the converse, if the original statement is P implies Q, the converse is Q implies P. Okay? And importantly, the converse is logically independent. Okay, it's logically independent of the truth of the original statement. So for example, it is raining implies the grass is wet. That does not necessarily mean that the grass is wet implies that it is raining. Okay, so for example, the grass could be wet because of a sprinkler. So the converse of the original statement is logically independent. There are certain instances where the converse is also true, and in this case, it leads to something called an equivalent statement, and I'll get into that in a bit more detail later on. The inverse of the original statement is not P implies not Q. This, similarly, is logically independent of the original statement. And we'll see why that is the case in a moment when I introduce the concept of the contrapositive. Okay, so we have now the negation. The negation is essentially the opposite of the original statement, and so this is logically opposite the original statement. So in this case, it would be P implies not Q, and I'm using this dash, which we normally use in probability and set theory terms, to represent the complement as the negation. Okay, so if it is raining implies the grass is wet is the original statement, then the negation is it is raining implies the grass is not wet. Okay? And this is logically opposite the original statement. Logically opposite. Okay? And I might just change the color of this to yellow if I can. Is that possible? No, that's okay. Okay, so the contrapositive now is flipping it around, so taking the converse and then taking the inverse of the converse. Okay, so it is, in this case, it is not Q implies not P. Okay, and the contrapositive is considered to be logically dependent on the original statement. Okay, so if the original statement is, or we also refer to this as logically equivalent, if the original statement is true, then the contrapositive is true. And if the original statement is false, then the contrapositive is also false, and also vice versa. So if the contrapositive is true, then the original statement is true, and so on and so forth. Okay? So we can see that a statement and its contrapositive are logically equivalent and logically dependent on one another. And that's also why the inverse and the converse are both logically independent, because the inverse is essentially the contrapositive of the converse. I hope that makes a bit of sense. Now, when we talk about equivalent statements, what we mean is a statement that has double arrows here. So what I mean here is this is a case where our original statement is true, and our converse is also true. So note that normally our converse is logically independent of the original statement, but in the case where the original statement and the converse are both true, in that case we consider it an equivalent statement. So an example of an equivalent statement is, if my heart is beating, then I am alive. Okay? So the original statement here is true, and similarly the converse statement, I am alive, implies my heart is beating, is also true. Okay, so in this case I have an equivalent statement. In this case both the original and the converse are true. Okay, so that's an example of an equivalent statement. Okay, so in this case here I have introduced what an implication, converse, equivalent statement is, a negation, an inverse, and a contrapositive are. I've also introduced these symbols here, the implication symbol and the equivalent symbol. And okay, that's fine. I will introduce these as well over the course of when I go into some examples of proofs. Okay, cool. So let's move into an example of a direct proof. So essentially what a direct proof is, you take your statement P implies Q, you take your statement P to be true, and then you show that Q logically follows. Okay, and so this is the essential aim of a direct proof. Okay, so one example is if A and B are even numbers, okay, then A plus B is even. Okay? And so this is the statement I'm required to prove. So when I'm trying to prove the statement, I put an RTP at the front here, and this is the formal way that I set up a proof. So RTP stands for required to prove, and I'm required to prove that if A and B are even numbers, then A plus B is even. Okay? I can also represent this in a slightly faster way using some mathematical symbols. So for all A, comma B, so this symbol here represents for all. So every number A and every number B are even numbers. A plus B is even. Okay? And now the next thing I'm going to do is I need to represent, how do I represent A and B as being even numbers? So that's the first step in my proof. And the way that I represent even numbers, what an even number is defined as is a number that is divisible by 2. Okay? So I can represent A, let A equal
2k, where k is an element of integers. Okay? And similarly, I can let b equal another number, 2l, where l is an integer. Okay? And so the reason I'm using a k and an l as two separate numbers, as two separate letters, is because they represent two different numbers. If I let a equal 2k and b equal 2k, all I'm showing is that a number plus the number itself is going to be even, not that any two even numbers when summed together are even. Okay, so that's why it's important that I use a k and an l in this case. And so here I've assumed that the initial statement p is true. This is me taking p to be true. And now what I need to do is I need to show that the conclusion, q, a plus b is even, also follows. And in order to do that, what I do is I do a plus b, and that's 2k plus 2l. And to show that it's even, I can just take out a factor 2, and this I know is going to be an even number because k and l are both integers. Therefore, a plus b equals 2k plus l is also an even number. Okay, and I've proven the statement. Another proof that we can use, so in this case what I've shown is the direct proof. The other proof is known as the proof by contrapositive, and it's a slight variation. Rather than proving the original statement, we prove it's contrapositive. And the reason why we can do that is because the contrapositive is logically equivalent to the original statement. Okay? So if P implies Q as the original statement, the contrapositive is not Q implies not P. Okay? And so a famous example where we might use the contrapositive is where we're trying to prove if n squared is even, then n is even. Okay? All right. So, in this case, it's a bit difficult to prove the original statement, going from n squared back to n. So what we can do instead is write up the contrapositive. And the contrapositive of this statement is for all n is even, n squared is even. Okay? So, in this case, what I do now is I prove, the contrapositive would be odd and odd. For all n is odd, n squared is odd. Okay? And so in this case, all I need to do is I need to prove the contrapositive. And if I prove that the contrapositive is true, that must necessarily mean that the original statement is true. And an odd number, first of all, is defined as a number that is not divisible by 2. And so the way I can represent an odd number is let n be equal to 2k plus 1, where k is an integer. Okay? So this is how I represent an odd number. Okay? So therefore, n squared is equal to 2k plus 1 all squared, which is equal to 4k squared plus 4k plus 1. And to show that this is an odd number, I just take a factor of 2 out, and I have the 1 hanging out the back. And because I know that k is an integer, I know that 2k squared plus 2k is also an integer. And so if I have 2 times an integer plus 1, that must mean that n squared is odd. Okay? And so therefore, the contrapositive is true, which means original statement is true. And as a result, I have proved what I wanted to prove. And so I can write a QED, quod erat demonstratum, which means what was to be proved has been proven. Another thing I can do is I can represent with a box like this, or a coloured in box like this as well. Okay? Importantly, you only need one of these. Cool. Another important thing I need to go over is examples and counterexamples. Okay, so in the previous slide, in terms of proofs, what I went over were for all statements. That is, for a specific number, it is always true that something else follows. Okay, there are examples where we might use there exists statements. And so for there exists statements, we can say there exists an odd number, for example. To prove there exists statements, we only need to give one example. Okay, so an example of an odd number in this case is 3. And so by providing the example 3, we have proved that there exists statement that there exists an odd number. In the case of for all statements, we need to go over a formal proof as we did before. But to disprove a for all statement, all I need to do is show a counterexample that shows that it's not true for all values. Okay, so an example of a for all statement that I can disprove is for all real numbers A. Okay, so A is an element of R, real numbers here. For all A is an element of R, there exists a B is an element of R such that A, B is equal to 24. Okay, and so at first glance it may seem like this is an actual true statement. For example, if A is 1, then B must be 24, and so there does exist a B such that AB is equal to 24. But an example that does not obey this is A is equal to 0, because there is no number B that can be multiplied to 0 to give 24. And so when we're thinking about counterexamples, a very common counterexample that we give for a lot of numerical statements is the number 0. Okay, so A equals 0 is the counterexample. Okay, so remember, for there exists statements, we need to only give one example to prove that it is true, whereas for all statements, we need to give a counterexample to disprove, or we need to go through a formal proof process in order to prove that it is true. So we've gone over this, we've gone over proof by contradiction, we've used implications and equivalences, quantifiers, examples and counterexamples. Okay, we haven't done proof by contradiction. So the last thing I'm going to knock off is proof by contradiction and also proving simple results involving numbers. So the most common example of a proof by contradiction is irrational number proofs. Okay, and so what an irrational number is it's a number that cannot be expressed as a fraction. When we are considering a proof by contradiction, what we usually do is we assume a certain statement that allows us to sort of make some mathematical steps and show that those mathematical steps lead to nonsense that contradict our initial assumption. Okay, so if we have, when we're talking about irrational number proofs, we can, for example, say root 2. Root 2 is an irrational number. So let's say we are required to prove that root 2 is irrational. Okay. In this case, what we do in our proof by contradiction is we assume the opposite. Okay, we assume the negation. Assume that root 2 is rational. And what this assumption implies is that root 2 can be written as a fraction of p over q, where p, q are integers, and they are not divisible by each other. And so the way that we represent them not being divisible by each other is p and q are co-prime. Okay, so they do not share a common factor. And this here is the most important statement in proving that root 2 is irrational. This statement here is what allows us to show that assuming root 2 is rational leads to mathematical nonsense. So if root 2 implies p over q, if root 2 equals p over q, that means that 2 is equal to p squared over q squared, which implies, in turn, that p squared is equal to 2q squared. And therefore, p squared is divisible by 2. And so, p is divisible by 2. Then we can write p as 2k, where k is an integer. And substituting this value for p equals 2k back into our initial equation, we have root 2 is equal to 2k over q, And so 2 is equal to 4k squared over q squared, implying that q squared equals 2k squared. And so q squared is divisible by 2, which implies that q is divisible by 2, which is a contradiction. Because here we've shown that p is divisible by 2 and q is divisible by 2. But according to our initial assumption, p and q do not share any factors. So herein lies a contradiction. Namely, that p and q should be coprime. And as a result, since we have shown that our initial statement that root 2 is rational leads to mathematical nonsense, we must accept that root 2 is irrational. And we have proved what we wanted to prove. And this sort of logic here, this setting out, is the sort of working that you should expect for a lot of irrational number proofs. It's essentially the exact same process that you follow each time. So, in this video, we have gone over mathematical statements and conditional statements, as well as their variations. We just went over proof by contradiction and proving results, simple results involving numbers. We talked about the importance of examples and counterexamples in the context of for all and there exists statements. And we also introduced symbols for implication and equivalence. There are several more symbols that you can use to represent mathematical statements, and it's really important that you practice writing proofs and writing those statements. And I think there are several examples of that in the Sadler textbook. So you can have a look at that, and the chapter in question I will link in the description below. Thanks for watching this one, and I'll see you in the next one.